Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 2, Lesson number 3 on even and odd functions. This is a relatively new topic for most students, and it's a brand new topic for students in my course. So let's jump into it and learn how certain functions are classified as even or classified as odd. All right. So even and odd functions have a very simple definition, as many functions do in math, right? An even function, or a function is known as even, if f of negative x is equal to f of x, all right? These functions display symmetry across the y-axis. This equation can be interpreted as opposite inputs give the same output. So if we have an even function, all right, and let's say f of 7 was equal to 2, then we would also know that f of negative 7 was equal to 2. So opposite inputs give the same output. Now, of course, that means that you've got symmetry across the y-axis, because if I went to 1, 2, 3, 4, 5, 6, 7, 1, 2, 1, 2, 3, 4, 5, 6, 7, 1, 2, then obviously that's reflected across the y-axis. You know, if I knew that f of negative 10 was equal to 17, then I would know f of positive 10 was equal to 17. So that's an even function. Simple enough. An odd function, or a function, is known as odd if f of negative x is equal to negative f of x. These functions display symmetry across the origin. This equation can be interpreted as opposite inputs give opposite outputs. So if a function is odd, right, and let's say I knew that f of 8 was equal to negative 3, then that would tell me that f of negative 8 would be positive 3. Okay? Opposite inputs give opposite outputs. Now again, it's got what's called symmetry across the origin. Let's see if we remember that, and let's talk about these 2 points. Well, if I went to 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, right, I'd have the point 8, comma, negative 3, and 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, and here would be the point negative 8, positive 3. Symmetry about the origin is this idea that if I connected this with a straight line and then I rotated it 180 degrees in either direction, not the best picture on earth, it would land right there. So not all functions are even, not all functions are odd, not all functions are even or odd. There's a lot of functions that are neither, okay? But certain functions can be classified as one of these two. And we're now going to get into some problems that looks at that. Anyway, I'm going to clear out the text, so pause the video if you need to. All right, here we go. Exercise 1. Given the following simple functions, determine if they are even or odd, then sketch a graph of each showing its symmetries. So these are probably pretty obvious because I've chosen literally the simplest functions I can think of. All right, but given the fact that I say figure out whether it's even or odd, that implies it's got to be one or the other. Okay, so what I can do is I can test. Testing is a good way to get a feeling for it. So maybe I'll test x equals 3 and x equals negative 3. Right? So if I do f equals 3, obviously I'll get 3 squared and I'll get 9. And if I do f equals negative 3, I'll also get 9. So notice opposite inputs, 3 and negative 3, gave me the same output. And so therefore this one is classified as an even function. All right. In fact, its graph, right, is the graph of the classic parabola. All right, and it's got that symmetry across the y-axis. 3, 9 is symmetric with negative 3, 9. Now likewise, we can do x equals, or g of x equals x cubed. Again, it's a good idea to test. Say that we take x equals 3 and x equals negative 3 again. Well, g of 3, which is 3 cubed, is positive 27. And g of negative 3, which is negative 3 cubed, is negative 27. So notice now, opposite inputs gave us opposite outputs. And therefore, this is known as an odd function. Y equals x cubed is a graph that you should know. All right, so add it to your list of functions that you absolutely positively should know. Whoops, that didn't work. My bad, that should have gone through the origin. And again, it's this idea that we've got the point 3, 27, 180-degree rotation, and we've got the point negative 3, negative 27. All right. Now, it's because of power functions that we then get the term even and odd. So any power function, remember power functions have the form y equals a times x to the b. This is a power function. All right. Anytime b is odd, we have an odd function. And anytime b is even, we have an even function. So that's where the names come from. But don't get me wrong, there's lots of even and odd functions that don't have anything to do with power functions. A good example are the sine and cosine functions. The sine function is odd, the cosine function is even, but they aren't power functions. All right, well, pause the video now and write down anything you need to, and then I'm going to clear out the text. All right, here we go. Okay, exercise 2. Algebraically decide if each of the following functions is even, odd, or neither. And actually, let's just do this. Let's just decide. Let's not worry about that algebraically. We're going to come back to an algebraic approach later. But let's just decide. And what I'd like you to do is pause the video now and test each one of these functions with opposite inputs. I would suggest keeping the numbers small, and that will give you a good sense for whether the function is even, odd, or neither. All right, let's go through it. In each case, what I'm going to do is I'm going to test the values x equals 2 and x equals negative 2, keeping the values small. So if I do f of 2, I'll get negative 5 times 2 plus 3 times 2 cubed. That gives me negative 10. 2 cubed is 8, so that's going to be 24 equals 14. Now let me do f of negative 2. Negative 5 times negative 2 plus 3 times negative 2 cubed. That's going to give me positive 10. That's going to be negative 8 times 3, which is going to be negative 24. That's going to be negative 14. Now notice, opposite inputs gave me opposite outputs. So this is an odd function, or at least the evidence supports that it's an odd function. But let's take a look at b, right? Again, we're going to test these two values all the way across. So if I figure out g of 2, that's easy. 10 minus the absolute value of 2 gives me 10 minus 2 gives me 8. And g of negative 2 gives me 10 minus the absolute value of negative 2 gives me 10 minus 2 gives me 8. Notice now opposite inputs gave us the same output, so that's even. All right, let's do this last one. It almost looks like an h. h of 2. 2 times 2 squared minus 4 times 2. 2 times 4 is 8 minus 8 is 0. Well, let's do negative 2. h of negative 2 is 2 times negative 2 squared minus 4 times negative 2. Negative 2 squared is 4 times 2 is 8, but then that's 8 plus 8, which is 16. Now notice those two outputs are neither the same, equal, nor are they opposites. So that definitively tells us that this is neither even nor odd. Neither even nor odd. All right, well, pause the video and copy down anything you need to before we go on and work more with the idea of even and odd functions. All right, let me get rid of them. Okay, next problem. Exercise 3. Selected values of the function y equals f of x are shown below. Given that f is defined at all values shown, and that is important, f is defined at all values shown, fill in as much of the table as you can given that f is either odd or f is even. So in this case, I'm telling you that f is odd. In this case, I'm telling you that f is even. Why don't you go ahead and pause the video and fill in those tables as much as you can. All right, let's go through it. Letter A, it's odd. Now, if it's odd, right, what that tells us is that f of negative x is equal to negative f of x. All right, so let's take this. We know that f of negative 3 should be negative f of 3. Well, f of negative 3 is 5, so f of negative 3 should be negative 5. All right. Opposite inputs give us opposite outputs. Well, how about this? We've got 2, right? 2 is equal to negative 4, so f of 2 is equal to negative 4, so f of negative 2 must be positive 4. Let's see, f of negative 1 is negative 7, so f of 1 must be positive 7. Now, f of 0, all right, that's a tricky one, okay? That's a tricky one. We'll come back to that one in a second. Let's leave it alone for a second. Let's go over to the even functions, okay? So even functions are defined by f of negative x equals f of x. So it doesn't matter whether the x I put in is negative or positive, I get the same output. Well, that's pretty nice. That means that negative 3 as an input gives me 5. That means positive 3 must also give me 5. Yeah, now it's simple, right? Positive 2 gives me negative 4. Negative 2 gives me negative 4. Negative 1 gives me negative 7. Positive 1 gives me negative 7. And again, f of 0 equals, All right. Now, in both cases, the function is defined there. All right. But in only one of the two cases can we actually give a value for f of 0. Think about that for a minute. One of them we're just going to have to say, I don't know, it could be anything. The other one we can definitively say is equal to something. All right. Well, hopefully you figured it out. F of 0 has to be 0 if the function is odd and it's defined. That's key. But in the case where a function is even, we really can't fill that out. Big time question mark. Now, the reason that it must be 0, right, is think about this, right? It's got symmetry about the origin. It's got symmetry about the origin, okay? That means it's got to be at 0, because if it were, let's say, 0, 7, right? So think about that for a minute. That'd be like 1, 2, 3, 4, 5, 6, 7. Well, then symmetry about the origin would mean there would also have to be a point at 0, negative 7. But that means it would be not a function, right? Wouldn't be a function. The only way that we can have symmetry with respect to the origin is if 0, 0 is on the graph. Now again, that's given the fact that f is defined. You can certainly have odd functions like 1 over x. That is an odd function. Y equals 1 over x is odd, and yet it doesn't go through the origin because it's not defined at x equals 0. Now, on the other hand, even functions, we don't have any clue, right? Even functions have symmetry across the y-axis. But that doesn't tell me anything. I mean, if the point 0, 7 is on there, well, fine, the point 0, 7 is on there. Absolutely nothing I can do about it, okay? So with an even function, we don't know what the y value is when x is 0 in this case. All right, pause the video now, think about it, and then I'm going to clear out the text. Okay, here we go. Let's go on to the back side of the sheet. All right, so exercise 4. I give you a graph of g of x, shown below, and we're going to give rough sketches of the following graphs. So this is actually just a little bit more transformation work. All right, And it really gets into reflections in the y-axis versus reflections in the x-axis. Now, we already learned that negative f of x is a reflection in the x-axis because we're negating y, and that's flipping it over the x-axis. On the other hand, f of negative x, well, that's going to be a reflection in the y-axis, right? The idea here is that if I take all the inputs and I negate them, right, then all the negative x's will become positive, all the positive x's will become negative, and the graph will literally flip its orientation with respect to the y-axis. Okay? So given that I have these graphs, how can I graph all three of these other functions? Pause the video now and see what you can do. All right, let's go through it. Well, g of negative x, this isn't so bad. All we have to know is that that is a reflection in the y-axis. So what will I do? I'll take this graph. Yeah, I'll keep in blue. And I'll just shift it. That point will come here. Maybe this point will go here. This point will go here. This point will come out here. And this stretch is down here. So I'll get something that looks like this. All right. So that's letter A. Let me switch colors. Let me go over to red. This is a reflection in the x-axis, which is kind of cool. This point doesn't go anywhere. This point comes down here. This point goes here. This point doesn't go anywhere. And this point's up here. One thing that's kind of cool is to track that 1, 4. In this case, it would go down to 1, negative 4. In this case, it would become, where is it? That's the blue. Let me write it back in blue. In that case, that would become negative 1, 4. All right, let me do one last one. I'll do it in green. Sorry, that'll be a little bit obnoxious. But what is this really? This is negative g of x plus 3. So this is first a reflection in the x-axis, followed by an upward shift by 3 units. Now think about that for a second. I flipped this thing over. Let me draw it in, well, actually I already have it in red, right? I already have that reflection in the x-axis. I just now need to shift it up 3 units. So it looks something like that. Not the greatest graph on earth, sorry about that. Think about it though, this point now would be at 1, negative 1. It used to be at 1, negative 4, but then I shifted it up 3 units. All right, well, I'm going to clear out this beautiful looking graph in a moment, so write down anything you need to. All right, here we go. Switch black to blue, and let's go on to the next page. All right, exercise 6. Show that this function is odd. Oh boy. Show. Now, we can't do this by example. Okay, the only time we can really do an example is when we've got a scenario where we're given a function, we're told it's either even or odd, then we can use examples to figure out which one it is. But here it says show the function is odd. Okay? Now there's only really one way to do that, and that means that we need to show that h of negative x is equal to negative h of x. All right? So it's very, very straightforward in a certain sense. We just have to show this. So then our first step is to figure out what h of negative x is. But as long as you know function notation, what that means is everywhere there's an x, I'm going to replace it with a negative x. All right, and then I'm going to simplify. Now negative x times negative x is positive x squared minus 1 divided by negative 3 times x. But that's the same as negative 1 times, x squared minus 1 divided by 3x, but that's negative 1 times h of x. So we did it. We proved that it was odd. That's really all you ever have to do. And to prove something that is even, we would put the negative x in and try to prove that it was equal to positive h of x. All right. Write down what you need to. I'm going to clear out the screen, and then we'll do the last problem. All right, here we go. All right, I love this one. Is the sum of two odd functions odd, even, or neither? What about the product of the two odd functions? Justify your answer algebraically. Well, one way to think about this problem is to grab two very simple odd functions like f of x equals x cubed and g of x equals x to the fifth, and then add them and multiply them and see what happens. But you can really do it more generically. Watch. I'm going to let f of x be an odd function. All right, what does that mean? That means that f of negative x equals negative f of x. I'm going to let g of x be an odd function, which means g of negative x is negative g of x. So now let's investigate the function f of x plus g of x. Right? That's the sum. All right. Maybe even give it a new name. We'll call it h of x. Okay. So is h of x odd, even, or neither? We know that when we add an odd number to an odd number, we get an even number. Maybe it works as well with functions. All right. So let's do it. Let's figure out what h of negative x is. Well, by definition, function notation, that's f of negative x plus g of negative x. And that's negative f of x plus negative g of x. So is that even or odd? Well, it depends on how it compares to h of x. We can factor a negative 1 out, and we'll have f of x plus g of x. But that's negative 1 times h of x. So h of negative x is negative 1 times h of x. Therefore, the sum of an odd and an odd is an odd. All right, let's talk about the product. All right, come up with a new function. Let's try k of x. Man, I just cannot get these all to look like x's. There we go. K of x, let's call that f of x times g of x. And let's investigate what k of negative x is. Question is, even, odd, or neither? All right, well, k of x, just by definition, will be f of negative x times g of negative x. But then that's negative 1 times f of x, because f is odd, times negative 1 times g of x, because g of x is odd. But I can do a little bit of arranging and do negative 1 times negative 1, giving me positive 1, and then just get f of x times g of x. But that's just k of x. So k of negative x is equal to k of x, and therefore that's even. Now, isn't that a little counterintuitive? It certainly doesn't work the way that numbers work. You know, if I add an odd to an odd, I get an even. If I multiply an odd by an odd, I get an odd. And here it's the absolute reverse. An odd function plus an odd function is an odd function. So the odd functions are closed under addition. See, got closure in there. On the other hand, an odd function times an odd function is an even function. So definitely not closed. All right. Pause the video now, write down what you need to, and we're going to move on. Okay, here we go. Let's finish up the lesson. So today we saw yet another way to classify certain, not all, but certain functions, right? An even function is a function that doesn't care about the sign of its input. Negative x, positive x give me the same thing, right? Opposite inputs give me equal outputs. On the other hand, odd functions have the property that opposite inputs give opposite outputs. So an input of negative 5 will have the opposite y value of an input of positive 5. Then there's lots of problems that go along with that. All right. For now, though, I wanted to thank you for joining me for another Arlington High School Math 4 Honors lesson. Until next time, my name is Kirk Weiler. Keep thinking and keep solving problems.